Hello! What I'm going to do today is a video with an overview of curved mirrors. So we have three different types of curved mirror problems that we work with. The first is concave real, the second concave virtual, the third convex virtual. So those three types are the three that we're going to be working with when we solve curved mirror problems. So I'm going to go through what they mean and the best process for solving the problems to get the right answer. And that's what you want, right? You want the right answer because then you understand the physics. So we have three types, and these two words each mean something physically. So concave, that means we have a concave mirror where the mirrored surface is on the inside. We represent that with this kind of curve. And concave means that we have a positive focal length, because the focal length is defined by the shape of the mirror. So when we have a mirror like this, we have a positive focal length. When we have a convex mirror, where the mirror is mirrored on the outside like this, then that's a convex. And again, based on the shape of the mirror, we know that that has to have a negative focal length. So concave and convex tell us something about the sign of the focal length and the shape of the mirror. Real and virtual, those are the type of images that we have. We have a real image if all the light that reflects off the mirror comes to a point and you could put a piece of paper there and actually see something on the paper. Virtual images are where the light tends to diverge away, but our eyes are really good at following where those rays would come from if they didn't bend or reflect at the mirror. Real images, again, this tells us something about the signs. A real image has a positive image distance, and that means that we have a real image, positive DI, on this side of the mirror, in the front of the mirror. Virtual has negative DI, negative image distance, and it's virtual because the image is back here, behind the mirror. And if you think about it, we can't have light actually hitting behind the mirror. So if you put a piece of paper behind the mirror, well, it's not going to do much, is it? So these are the three types, and these two words each tell you something about the sign of the focal length or the sign of the image distance. So the first thing you want to do when you are presented with a problem, so you might have something like this, step one is to identify the type you're working with. So what type of problem is it? All right, so I see that this is curved in like this. So this is concave, this one's concave, and this one's convex. And now real or virtual? How can we tell that? The only convex images we get are virtual, so that one's easy. These are always virtual with a convex mirror. But with concave, how do we tell? The way you can know if it's going to be a real or virtual image is to look at where the object is. If the object, like the light bulb or whatever it is we're looking at, is farther away than the focal point, then we have a real image. If the object is within that focal length, then it is virtual. So that is how you identify what type of mirror problem you're going to be encountering. Concave or convex based on the shape, and virtual or real based on where that image is based on that focal length. So that is step one. Step two. We will always be given the focal length of the mirror. But to draw our rays, what we do is we need to draw the center of curvature. And the center of curvature is always double the focal length. So I very conveniently made these mirrors at 10 centimeters focal, which means my center of curvature is at 20. So there's my 10. I'm going to mark that for all of them. So there's 10, there's 20. All right, so that's our next step because we need this center curvature point in order to draw the rays. We got that step done. 3. So 3 is draw the 3 rays, 3 and 3, I guess. draw the three rays. And we have pretty much the same three rays for every situation, but how they look is a little bit different. So the first ray is one that leaves the object parallel to the axis and then hits the mirror. All right, so leaves the object parallel to the axis, so it's going in like this, and then it bounces off the mirror through the focal length. Okay, so this ray of light, and remember that light is being emitted in all directions from this source, this ray of light is going to go boom, and it bounces right through that focal length. And we can do that for all three. So I've got something, and when you're doing this, really what you want to do is you want to be drawing to a straight line at the back of the mirror. All right, so I'm going to draw, a tiny little thing out. So it's going out parallel to this axis, and then it reflects off the mirror through the focal. Okay, that leaves like that. Our third one, all right, so it goes out parallel to the axis, and then it reflects off through the focal. So it bounces off, because it's bouncing off this reflective surface, but the way it bounces off is through that focal length. All right, so this one looks kind of like that. Okay, so that's our first ray. It comes off of the object parallel to the axis, and then it reflects off the mirror in a line with the focal length. Our next one is something that comes off of the object and lines up with the focal. So it comes off of the object and hits the mirror lined up with the focal. And then it bounces off parallel to the axis. And I'm not expecting my numbers to look very good here. Not at all. Okay. Then what do we have? All right, so now we have the object here. And see, this one tends to be a little weird for people because we have something that goes out here. It goes through focal and then hits the mirror. Here, the order is just reversed. We have something that lines up the focal and the object. Ooh, something like that. So we line up the focal and the object, and then it bounces off that mirror parallel, oh boy, to the axis. Something like that. So that one tends to be a little tricky. The third one, convex virtual. All right, so we have something lining up the object and the focal, but as soon as it hits the mirror, it doesn't keep going through the mirror. As soon as it hits the mirror, it bounces back off. Let's see, something like that. Okay, so we aim a line connecting the object and the focal, and then as soon as it hits the mirror, it bounces off parallel. Line up the object and the focal, bounce off parallel. Line up the object and the focal, bounce off parallel. Our third ray is the one, the easy one, that goes through the center of curvature. So this is just one ray because it bounces off the mirror onto itself. So all we need to do is draw a line. So it's going to bounce off the mirror there, goes in, and then comes right back out. So just one line for the center of curvature. All right, so here we've got object, center, curvature, and then it's going to bounce off the mirror, so it's going in and out like that. Here, oh boy, there we go. So it's going in and then bounces off the mirror right onto itself. Whew. All right, so here we have the three rays that reflect off the mirrored surface. Now we want to find out where those rays meet. In this case, it's pretty clear that those three rays meet right here. So this is where the image is. Here's my object, and here's my image. My object is here, but where the heck is the image for this one? Where do the three rays that bounce off the mirror converge? Where do they meet? Well, if you think about it, we've got these three rays. If they meet up, I'm going to guess they meet up somewhere back here. So what we do now is, if we need to, we trace backwards, what I call back tracing, any rays that leave the mirror. So back trace the rays leaving, oops, sorry about that, the mirror. And what do I mean by that? Well, I'm just going to keep this light ray, our eyes think that it comes from something along this line, so somewhere on this line. Same thing here. This light ray, if it gets into our eye, we think it came from something along this line. So I'm going to, all right, trace backwards the ones leaving the mirror, just the ones leaving the mirror. And I usually do this in dotted lines just to remind myself that the light isn't actually here. And I can do that here as well. Oh boy. So this one, oops, lines up with F. So the light isn't actually existing behind the mirror. It can't get through the mirror. But we need to know where our eye gets tricked into thinking that it is. Okay, something like that. And then something like this. And then the center curvature. That one's the easy one because it's just one line. It keeps going up like that. Here, I'll make it dashed. There. Okay, so here we're going dashed through the center curvature. Okay, so we back traced the rays that are leaving the mirror, and that's why I find it really helpful to draw arrowheads on the ones that are leaving the mirror, because that tells me which ones to back trace. I actually have 1, 2, 3, 4, 5 rays that I could trace backwards. I only want the ones that are leaving the mirror. So now, where do the 3 rays meet up? Well, somewhere around here. Okay, so my image is somewhere around here. And somewhere around here. All right, so I've got my rays traced, and I find where they're meeting. So that's my step 5. Find where the rays meet. And that is where your image is formed. So I usually just put a dot there. You can put a little eye saying image if you want. And what is next? Okay, 6. We are going to measure everything. Measure all. And I'm going to pause. Okay, we're back. This is why I should turn off my phone. All right, what were we doing? We were measuring everything. Measuring all. Okay, so what are we going to measure? And I'm going to do some erasing here. I'm going to, I guess, erase this one. Yeah, because we can measure a whole bunch of different things, and we will, but we have to be careful with the signs, the positive, negative signs of the stuff that we are measuring. The typical table that you're going to see on an assessment is going to ask you to figure out a whole bunch of different things. So we're going to start off with DO, which is a measured quantity, and then the focal length, which is measured, DI, image distance, measured, the image distance calculated, the height of the object, which we measure, the image height measured, the image height calculated, and the magnification. So you're going to have, along with the picture, a table like this that you are going to be filling in with the, hopefully, correct numbers. So what we've got is, I wish I had a different color here. Okay, so the things we measure, the object distance. Object distance is object to mirror. And that is purely the horizontal distance. So that is just from here to the mirror. So object distance is from that object to the mirror. And this is always going to be positive because we are always going to have an object that's in front of the mirror. Our image distance is the same horizontal thing. Oh, I gotta move some of these around. So our image distance is image to mirror. So DI is this right here. Our focal length This could be positive or negative. Our focal length is, again, horizontal distance. The F is mirror to the focal point. And that could be positive or negative. DI calculated, well, that should be the same as this. HO, so the heights. Well, HO, the height of the object, is going to be from the object down to our axis, or up to our axis. The height of the image, HI, is going to be, again, just purely up-down height from image to axis. These can be positive or negative. M is the magnification, could be positive or negative, and that one again can be positive or negative. So what about the signs here? If we have a mirror, let's see, it doesn't matter if it's concave or convex. If we have a distance measured on this side, it is positive. So this is a positive distance measurement in front of the mirror. Anything behind the mirror is negative distance, whether it's DO or DI. In terms of height, well, above our ground level, our axis, is a positive height. Below is a negative height. So here we'd have a positive height. Here we'd have a negative height. Positive height, negative height. And so depending upon which quadrant you're in is going to tell you what your sign is for DO, DI, and for HO, HI. So what we've got here, I would say, is a positive object height, because I'm going up. Here is a negative image height, a positive DO, because I'm in front of the mirror, a positive DI, because I'm in front of the mirror. And I'm in front of the mirror for F, so that's positive as well. Here, my object was in front of the mirror, positive DO. My image is behind the mirror, negative DI. My height of the object were below, so a negative object height and a negative image height. If I do some measurements on this one, let's see what I would get, and then you can actually do the calculations. Centimeters. All right, so DO, how far are you from the mirror? Well, we're just about 30. I'm going to say that's a plus 30. The focal length I set at 10. The DI, image distance measured. That's from here to here. And now it's positive because it's in front. 15. Plus 15. We're going to calculate that. HO, the height of the object. That's this right here. 7, and it's up, so plus 7 centimeters. Height of the image, down, so what do I have here? 1, 2, 3, 4. Negative 4. We're going to calculate that and calculate that. For the second, let's see if I can get this all on here. For the second one, let's see what we've got. My object distance from object to mirror, 1, 2, 3. That's always positive. My focal was plus 10. I'd set that earlier. DI, from my mirror to my image. It's behind, so it's negative. And we're at something between 4 and 5. I'm going to say something like negative 5. HO, height of the object. We're below the axis, so it's negative, and it's about negative 5. HI, below the axis, we have negative 7, maybe. So there we have our measurements. And use this, feel free to write this on your equation sheet if you want. Use this to tell you what the signs of these are. Then, what you do after you've measured everything is do the calculated values. So the first thing you're going to do is calculate DI. So we're going to use DO and F to calculate DI. Then once we have DI, we can get the magnification. So next up is magnification. Once we have magnification, we can get HI. So those are the three that we can calculate. And then as a last step, you always check, remember, make sure your answers make sense. These two are the same thing. They should be pretty close. If you got 14 here, that's pretty close. If you got, negative 4.1, that's pretty close. And then these two are the same thing. They're both the height of the image. So this one that you calculate should be around negative 4. If it's around, negative 3.8, negative 3.2, negative 4.6, somewhere around there, hopefully. The better you're drawing, the closer these two are going to be. So if you do this right now and calculate this and this and this, I have a really sloppy drawing. You might be kind of far off. When you do this, I want you to be as precise as possible so that your numbers for DI are really close and your numbers for HI are really close. So once you've done that last step of checking, let me just put that down, and then 8, check your answers. Make sure they make sense. Are these close? Are these close? Are your signs all right? Once you've got that, you are done. So that is the way to deal with curved mirror problems. And I think we've got it all. So that should be a good overview for you to figure out how to solve these no matter which type they are. Concave real, concave virtual, or convex virtual. All right, that's all I got. Good job.